Welcome to part 2 of the Spring 2012 MT126 Statics Final Exam solutions. And problem 2 was a area moment of inertia problem. Started out with a cross section with an upper plate of 12 inches by 1 inch and a lower plate of 10 inches by 1 inch. Separated by two L4 by 3 by 1/4 angle standard shapes. The height of this leg is actually 4 inches, so we will put that in there. From here, we need to calculate the centroid of the shape. Need to decide on our reference axes. Since it is symmetric about the middle here, I'll choose this as one of our reference axes. So this becomes our y centroidal axis. Now our x is not as easy to choose because it is not symmetric about any horizontal axis. But so I usually come down to the bottom here and choose an initial reference axis along the bottom. Alright, so my first areas will be this will be 12 inches by 1 inch equals 12 square inches. Likewise, this will be 10 square inches. And we'll label these as our first and second elements, and the angles will be our third and fourth elements. In our references, we find that these angles have an area each of 1.69 square inches. Now, for the x-bar, the distance from the vertical centroidal axis to the centroid of the shapes, we start with zeros for the plates because they're located right on there. But the angled shapes, that's a little bit of a different story. Looking at the table, we find that the distance from here to its centroid horizontally is 0.725 inches. And it's going to be the same over here. So the total distance from here is going to be half of the 10, 5, minus 0.725. So this distance will be 4.275 inches. The other direction will be negative 4.275 inches. And that will come into play when we find the centroid. Now, the vertical centroids coming from the chosen horizontal axis here. For element 1, we have to go from this horizontal axis up 1 inch, up 4 inches, and then up halfway of the element we're looking for. So this distance is 5.5 inches. Okay. And then for element 2, it's pretty easy. It's only half of its height, going from the chosen reference axis. So that's half an inch. Now to the angled shapes, we go up 1 inch of the plate to their centroidal axis. Our references in the table say that the distance from the flat to its centroid here is 1.22 inches, so the total here is 2.22 inches. So we now have the distances from each reference axis to each of the centroids of each of the elements. We also have the areas of each of the elements. So our next step in finding the centroids is to add up all of the products of the areas times the distances to the centroids for each element, and divide those summations by simply the summation of the total area. We calculated areas again of 12, 10, and 1.69 inches squared for the angles. They added up to a total of 25.38 square inches. Our X bars are shown here. Obviously 0 for the plates, and the 4.275 distances. Notice that number 3 is negative. And of course, multiplying by 0 will get you 0. This one for element 3 came out negative. This one came out positive. So when we add them all up, they end up being 0, which is what we expected. That means that the centroid of the entire shape is right on the reference axis that we chose in the first place, which is what we had expected. Here are the y bars: 5.5, 0.5, and 2.22 for each of the angles. You multiply those by the areas of each, and you get 66, 5, 3 3/4, and 3 3/4. Add all those up, and you get 78.5. So when we add them all up and divide by the areas, obviously the x bar will be 0, and the y bar will be 3.093 inches. That means for the entire shape, the centroid is 3.093 inches up from the reference axis. If you used a different reference axis, then you'll have a different number, but it will come to the same location. Now, for the remainder of the problem, to find the area moments of inertia, it's first important to find the formulas for each of the elements. Of course, the formula for the rectangular portions is very simple, and you just need to look up the tables for the angled elements. So I will reveal the final answers there. Then one of the most tricky calculations is actually still simple. It is the distance from the centroidal axis. So if we make the centroidal axis in red here, and we found that to be 3.093 inches here. Okay, that's our centroidal axis, our XX centroidal axis. Quite a messy diagram here. So the distance y prime is from that x-axis to the centroid of the various elements. And I will leave those calculations to you, but that's simply 3.093 minus the 0.5, the 2.22, and the 5.5 inches. When you square that and multiply it by the various areas, these are the values that you get, and there is the total after you add up the solo portions and the parallel axis portions. Here you add them all up together to get that. Likewise with the area moment of inertia around the vertical axis, if the formulas and tables are very straightforward. After looking up and calculating them, these are the values we get. X prime again is the distance from this vertical axis to the centroids of each of the elements. In this case it would be 4.275 inches. The other ones are just zeros. You take the areas and you multiply by the square of the x primes here, and these are the values we get for the parallel axis portion. And then we add this column and this column, we get this column, add all these values up, and this is what we get. To finish off the problem, add up Ix plus Iy, and you'll get the polar moment of inertia. For the radius of gyration around the x-axis, simply take Ix, divide it by the sum of the areas, and take that, the square root of that, and you'll get that. Likewise with radius of gyration about the y-axis, take Iy, divide by the sum of the areas, that quotient, take the square root of that, and you will find the radius of gyration around the y-axis. So if you're doing the reworks, I expect to see all of these values and the work and the formulas all together.